mountains on a star. Can you imagine? But not just any star.
Yeah.
We're talking neutron stars, the densest things in the universe, besides black holes, of course.
Right.
I mean, a teaspoon.
Yeah.
A teaspoon of neutron star material
Yeah.
would weigh billions of tons.
It's crazy.
Absolutely mind-blowing. And that is what we are diving into today.
Okay.
All about these mind-blowing neutron stars and the possibility that they might have mountains. So we're looking at this article from SciTech Daily. It was published November 30th, 2024.
Wow. Very recent.
Yeah, just came out.
Okay. So these neutron stars.
Yeah.
They're remnants of massive stars that have gone supernova.
Right.
Basically, you've got a star much larger than our sun, collapses in on itself.
Okay.
And it's just crushed down to the size of a city.
Wow.
That's how dense we're talking.
It's hard to even wrap my head around that kind of density.
Yeah.
To think that they might have mountains on these things.
Well, mountains might be a bit of a misnomer.
Okay.
Because of the intense gravity.
Yeah.
A neutron star, anything that resembled a mountain,
right,
it would be more like a tiny bump.
So like basically
insignificant.
On a cosmic scale, like barely noticeable.
So how would we even know they exist?
Right.
If they're so small. How do we know about these things?
That's where the incredible science of gravitational waves comes in.
Oh, okay.
So imagine the fabric of space-time like a stretched sheet.
All right.
Okay.
Right.
Now picture a neutron star. Incredibly massive, spinning rapidly, creates a dip in this sheet.
Okay.
As it spins, it sends out ripples.
Ripples?
Like you dropped a pebble into a pond. Those are gravitational waves.
Okay.
Even tiny bumps on a neutron star can create these ripples.
So even though they're minuscule, compared to the star itself, because of its enormous mass and spin,
exactly,
those tiny imperfections could still create detectable ripples.
Exactly. In space-time.
Wow.
That's wild.
Yeah, and detecting those ripples is a monumental task.
I bet.
Observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory.
Okay. Can you tell me more about that? What is that?
Essentially, LIGO uses this principle called interferometry to detect these incredibly faint signals.
All right.
So imagine two beams of light traveling down perfectly straight paths.
Okay.
When a gravitational wave passes through, it distorts space itself ever so slightly, changes the length of those paths.
Gotcha.
LIGO is designed to detect these minute changes. Which it's like trying to measure the width of a human hair from thousands of miles away.
So it's
be hard.
Very precise.
Yeah.
So scientists are using this technology, trying to find these gravitational waves coming from these neutron stars.
Yeah.
But the mountains themselves are so small.
Yeah.
It sounds like we're trying to find a needle in a cosmic haystack.
It's definitely a challenge. But the potential payoff is enormous.
Right.
Finding continuous gravitational waves from neutron stars would revolutionize our understanding of these objects and provide us with a whole new way to observe the universe.
It's like we're developing a whole new sense, being able to hear the universe through these gravitational waves. But if they're so difficult to study directly, how are scientists even getting clues about what's happening on the surface?
That's where things get really interesting. Scientists are finding these unexpected connections between neutron stars and some of the objects we see in our own solar system.
Wait.
Yeah.
Are you saying that studying things in our own solar system can help us understand what's going on with neutron stars billions of light years away?
That's right. Scientists are looking at icy moons like Europa, which orbits Jupiter.
Yeah.
And Enceladus, which orbits Saturn.
I know those moons.
Yeah.
They got those fascinating cracks and ridges all over their surface, right?
Exactly.
What do those have to do with neutron stars?
Well, those cracks and ridges are formed by the tidal forces exerted by the giant planets that they orbit.
Right.
Now, those forces are nowhere near as strong as the gravitational forces on a neutron star.
Right, of course.
But scientists believe that similar processes might be at play, just on vastly different scales.
So by studying how tidal forces shape the surfaces of these icy moons, scientists can gain insights into how the extreme gravity
exactly
of a neutron star
yeah.
might create those tiny mountains, or bumps, as you call them.
Precisely.
On the surface.
And it's not just icy moons that offer these intriguing parallels. Even Mercury, with its thin crust over a large metallic core, provides clues. The way its surface has buckled and shifted over time. Yeah. Due to internal pressures, might mirror in a very distorted way what's happening on the surface of a neutron star.
It's remarkable how scientists are drawing these connections between seemingly unrelated objects in our own solar system.
It's really fascinating.
And these distant, ultra-dense stars.
It is.
Makes you wonder how much more we might learn by studying our own cosmic backyard.
Absolutely. It highlights the interconnectedness of the universe.
Yeah.
How studying one phenomenon can illuminate another, even across vast distances and scales.
Absolutely.
But let's get back to those gravitational waves for a moment. You asked earlier what secrets they might reveal about neutron stars, and that's where things get really exciting.
Okay. You mentioned that finding these waves would be a huge breakthrough.
Yes.
What kind of information would they carry?
So think of gravitational waves as cosmic messengers.
Okay.
Carrying encoded messages about the objects that created them. By decoding those messages, we could unlock a treasure trove of information about neutron stars.
Okay.
For starters, we could glean insights into their internal structure.
Internal structure. But how can we possibly know what's inside a neutron star? I mean, it's not like we can just cut one open and take a peek.
You're absolutely right. That's what makes gravitational waves so powerful.
Okay.
They offer us a way to probe the unseen, to listen to the heartbeat.
The heartbeat
of these celestial objects.
So you can basically listen.
Yeah. By analyzing the specific patterns and frequencies of these waves, we could potentially learn about the different layers within a neutron star.
Okay.
Their composition, their densities, things we could never observe directly.
So it's like using gravitational waves to do a cosmic ultrasound on a neutron star.
That's a great analogy.
Okay, correct.
And it's not just about structure.
Okay.
We could also learn about how neutron stars behave. How they spin, how they interact with their surroundings. We might even be able to test some of the most fundamental laws of physics.
Really?
Like Einstein's theory of general relativity in these extreme gravitational fields.
Wow. So sounds like gravitational wave astronomy is opening up a whole new frontier in our understanding of the universe.
Yeah, it really is.
And all this stems from the possibility of tiny mountains on these incredibly dense stars. It's mind-boggling.
It really is. And it's important to remember that this is a very active area of research. Scientists around the world are working tirelessly to improve the sensitivity of gravitational wave detectors, to refine their analysis techniques, and to push the boundaries of what we can learn from these faint cosmic signals.
Wow. It's amazing to think about all that information encoded in these faint ripples traveling across the universe. Really highlights how much we still have to learn about the cosmos.
It certainly does. And each new discovery just seems to raise more questions than it answers. Pushing us to delve deeper into the mysteries of the universe.
It really is it.
That's what makes this research so captivating. Constant journey of exploration and discovery.
You mentioned earlier how scientists are drawing connections between neutron stars and objects in our solar system. Makes me wonder, are there any other unexpected links that we might uncover?
That's a great question. One area that researchers are particularly interested in is the connection between neutron stars and the formation of heavy elements.
Heavy elements? You mean like the ones we find here on Earth? Gold, platinum, uranium.
Exactly. Those elements are forged in the hearts of stars through nuclear fusion. But for the very heaviest elements, even the intense heat and pressure of a supernova explosion might not be enough.
So where do they come from?
That's where neutron stars come in. Some scientists believe that the collisions of neutron stars, those cataclysmic events that send out powerful gravitational waves, might be the cosmic factories where these heavy elements are created.
Wait, so the gold in my ring might have been created billions of years ago in a collision between two neutron stars.
It's an amazing thought.
That's incredible.
It is, isn't it? It connects us to these distant cosmic events in a profound way, reminding us that we are all made of stardust, forged in the hearts of stars.
Speaking of connections, let's circle back to the article we started with. Mentioned that finding these continuous gravitational waves from neutron stars would be a monumental achievement in astrophysics. But it also made me think, what if we could perceive these gravitational waves directly?
Okay.
Not just detect them with instruments like LIGO, but actually see them like we see light.
Now that's a truly mind-bending concept.
I know.
If we could see gravitational waves, our view of the universe would be transformed.
Right.
Imagine a night sky where we could see not just the stars, but the subtle ripples in space-time, the echoes of black holes merging.
It's incredible.
The whispers of neutron stars spinning at unimaginable speeds.
Wow. A universe of unseen forces made visible, a cosmic ballet of gravity revealed. In all its majesty.
It is, isn't it? It just highlights how limited our current view of the universe is. Based solely on the electromagnetic spectrum.
Right.
Who knows what wonders await us when we unlock the secrets of gravity? Learn to see the universe in a whole new way.
Well, on that note, I think we've reached the end of our deep dive into this fascinating world of neutron stars and their potential mountains.
Yeah, it's been great.
Covered a lot of ground today.
We have.
From the extreme density of these objects to the mind-bending concept of gravitational waves and the unexpected connections to objects in our own solar system.
Right.
And we also touched on the groundbreaking research being done to detect these elusive signals.
It's fascinating.
And the incredible insights they might reveal about the universe. So for all of you listening out there, here's a final thought to ponder.
Okay.
If we could develop a gravitational wave telescope, what would we see? What unseen wonders would be revealed? Keep exploring, keep questioning, and keep looking up at the stars.
That's great advice.
Until next time.